Welcome everyone. For today's prep, we're going to look at an example for figuring out the particular antiderivative of a function. And what we're going to see is that in order to do this, in order to find the particular antiderivative, we're going to need what we call an initial condition. And then later on, we'll see how we can use this strategy for problems involving position, velocity, and acceleration. But we'll get to that later. So for today's prep, we're just going to be kind of looking at particular antiderivatives. And if we remember back, all the integrals and antiderivatives that we've done so far have been finding the general antiderivative of a function. And what we're doing is we're actually finding all antiderivatives up to a constant. And then we throw a plus c at the end. And the reason why we do this is because, as we've seen, there's really an infinite number of possible antiderivatives that we could have for a function, but they all just differ by a constant. So rather than trying to distinguish between all these very similar functions, we just put a generic plus c at the end. So for our general antiderivatives, we're going to put plus c, as we've been doing. But now we're going to look at what we call particular antiderivatives. And for these, we're still going to be using plus c in our work, but then we're actually going to solve for what the c value is. So we're going to solve for plus c. And the way we're going to do this is, well, we're going to need to know a little bit more information about the original function that we're trying to recover. So we just need to know just a little bit, and we'll see what this is. And we're going to call that little bit of information an initial condition. Okay. So general antiderivatives, we put plus c at the end. Particular antiderivatives, we actually solve for c value. So we're going to try an example to see how this works. All right, so for example 1, we're going to find the particular antiderivative, function f, given that its derivative is equal to x plus 1 over square root x. And we have a little bit of extra information about the original function here. So we know that our original function value at x equals 1 is equal to 5. So this is what we call the initial condition. Okay. So we want to find the particular antiderivative of this function. So we're going to start with the integration process. So we're going to start by finding the general antiderivative. So we're going to integrate the derivative. So we know the derivative is equal to this function. So we know that if we integrate the derivative, essentially the integral and the derivative almost cancel out. And that should give us back the original function. So let's try out the integration. So we're going to have x plus 1 over square root x. And to help us with the integration, this isn't one of our basic form antiderivatives. We got to do a little bit of rewriting here. And our strategy, we've seen one like this before, when we have a fraction, is to actually do the division. So that's what we're going to try here. Whoops. So we're going to rewrite this using division. Okay. So let's take the x and the square root x. They're going to get their own fraction. And then we'll take the 1 and the square root x, and they'll get their own fraction. So we're just kind of breaking this up. And then we keep simplifying. So each of these fractions should, well, we can subtract the exponents. So what do we get for that first fraction? Well, there's a hidden exponent of 1 here. The square root kind of our usual strategy, we could rewrite that as x to the 1/2. So if we subtract the exponents, we have just x raised to the positive 1/2. And over here, we can rewrite that fraction using a negative exponent. So we end up with plus x raised to the negative 1/2. All right, so we've simplified. We've gotten each of those as a single power function now, so now we can just use our regular power rule. So for the first term, again, we've got our x to the 1/2 here, and we've got our x to the minus 1/2 here, and we just want to find the antiderivative of these. So we're going to do our power rule for each. So for the x to the 1/2, we're going to write down x, we're going to add 1 to the exponent, and then we're going to take that new exponent and flip it and put it in front. So we'll have a 2/3 in front. And then if we do the same thing for the x to the minus 1/2, well, the plus sign will stay in the middle. Our variable is x, so we write that down. We add 1 to that old exponent, so that's going to bump us up to positive 1/2. We take that new exponent and we flip it. So we have 2/1 in front, or just 2. And then as usual, whenever we find a general antiderivative, we put plus c at the end. So the first part of this is just finding the general antiderivative. And now the next step is to actually use that initial condition to figure out what the c value is. All right, so let's see how that works. So we're going to solve for plus c. All right, so we know that f of 1 should be equal to 5. So the idea here is let's take x equals 1 and plug it into the function that we have so far for f. So we're going to evaluate. So we'll plug x equals 1 into the first part. We get 2/3 times 1 raised to the 3/2 power. Whoops. And then we plug it into the second part, and we get plus 2 times 1 raised to the 1/2 power. And then we have our plus c. We don't know what c is yet. And we know then that this should be equal to 5. So whatever we get here, it should be equal to 5. And that's because our initial condition says when we plug x equals 1 in, we should get 5. So this is our initial condition that we're using. So the output should be 5, and then the x coordinates that we're plugging in are 1. Okay, so this gives us an equation that we can use to solve for c. So if we simplify this down, the powers of 1 are just 1, so we have 2/3 for the first piece, then plus 2 plus c equal to 5. And now this is just a nice equation that we can use to solve for c. All right, so let's try it. So subtract 2 from both sides, and then subtract 2/3 from both sides. And when we do that, we get c is equal to, if we subtract 2, we're going to get 5 minus 2, so 3. And then if we subtract 2/3, we'll have minus 2/3. And perfectly fine to just leave it like that. If we wanted to get a common denominator, though, and do the subtraction a little bit further, we would get that our c value here is 7/3. So 9/3 minus 2/3. So we know what the c value is, and this feels like it should be the answer, and it almost is, but now we just want to make sure that we actually put this in to our general antiderivative. So the last step is to get our particular antiderivative. And we're just going to plug C in. So plug in C. All right, so we found that the general antiderivative, little f of x, what was it? It was 2/3 x to the 3/2 power plus 2 x to the 1/2 power. And then instead of our c value, we actually know what c is. So we can put 7/3 here. And we have our particular antiderivative. So that's our answer. So you just want to make sure. It's really easy to get to this point, and it feels so satisfying. You get to c is equal to this. Just want to make sure you go that one extra step and actually then state what the particular antiderivative is. So the process for doing these is we start by finding the general antiderivative, which should include plus c at the end. Then we use our initial condition to solve for c. And the way we do that is we take the x value for our initial condition and plug it into the antiderivative that we found. And then we set the whole thing equal to the initial value. So in this case, the x value that we knew something about was x equals 1, and our initial value here was 5. So we plugged x equals 1 into our antiderivative, and then we set that whole thing equal to 5. And then that gives us an equation where everything is constants except c, so then we can just move the constants around and solve that for c. And then the very last step, just to plug back in. All right, so we're going to try a few more examples like this. So in class, we'll look at example 2, which is finding the particular antiderivative, and we'll see how to unravel the second derivative. And then later on, we'll see how we can relate this to problems involving position, velocity, and acceleration. So we'll see you then. Bye-bye.